Good morning, sir. Today we are here to explain our project titled Prediction of Road Pothole Using Convolutional Neural Networks. We are batch 11 and our team consists of 4 members, myself Vijay Shankar TV, Sendamar Selvan, Sengadir Selvan and Shiva K. We are doing this project under the guidance of Mr. Shaikh Hidayat Basha. Thank you, sir. Next slide. The objective of our project is to develop a deep learning model for road pothole classification by using convolutional neural networks for potentially classifying the results in the form of best accuracy by comparing the different architecture models. In our abstract, we are here to predict the presence of potholes on roads, which is one of the major cause of road accidents as well as wear and tear damages for vehicles. Recently, with an increase in the vehicular traffic and pollutions, the roads are getting filled with big and small potholes in almost every city in the country, which is one of the major cause of accidents in our country and all around the world. We tend to present a convolutional neural network in TensorFlow and Keras based road pothole classification. This proposed system is based on CNN using road pothole images to classify potholes. It is predicted that the result success will increase if the CNN method is supported by adding extra feature extractions from the images and successfully classifying the road potholes. To finally deploy this model, we are using the local Django framework.
In the survey of pothole detection using computer vision and learning, the technique used for identifying potholes on road surfaces aim at developing strategies for real-time or offline identification of potholes to support real-time control of a vehicles or offline data collection for road maintenance. In the, survey of pothole detection based on disparity transformation and road surface modeling, computer vision approaches are generally based on either 2D road image analysis or 3D road surface modeling. However, these two categories are always used independently. Furthermore, the pothole detection accuracy is still far from satisfactory. In the survey of detection of asphalt pavement potholes and cracked based on the unmanned area vehicle multispectral imagery, it tells that to improve pavement inspection efficiency, some new forms of remote sensing data without destructive effect on the pavement are widely used to detect pavement distress, such as digital images, light detection, and ranging and radar. My friend Sengadir Selvan will explain the existing system.
Let me explain existing system. We present a novel deep learning framework named the Iteratively Optimized Patch Label Interference Network for automatically detecting various pavement distresses that are not solely limited to specific ones, such as cracks and potholes. IOPLIN can be iteratively trained with only the image label via the expectation maximization inspired patch label distillation strategy and accomplish this task well by interfering the labels of patches from the pavement images. Moreover, it can roughly localize the pavement distress without using any prior localization information in the training phase. To better evaluate the effectiveness of our method in practice, we construct a large-scale bituminous pavement detection dataset named CQU-BPDD consisting of 60,059 high-resolution pavement images which are acquired from different areas at different times. Extensive results on this dataset demonstrate the superiority of IOPLIN over the state-of-the-art image classification approaches in automatic pavement distress detection, and the proposed system will be discussed by our teammate Vijay Shankar.
A better proposed system using a CNN is proposed by us. We are proposing a system that employs convolutional neural network as the deep learning technique. After collecting a suitable amount of data containing the images of potholes under various conditions and weathers, we are developing a model that is used to classify these potholes or plain roads. Both images are classified using this deep learning model. Also, a comparison between the self-built convolutional neural model and some of the pre-trained models are also done. The proposed method for this project is to train a deep learning algorithm deployed model capable of classifying and detecting road potholes along with the help of convolutional neural network based TensorFlow and Keras. Various road pothole images are used as datasets to build a model for classifying the potholes. It is predicted that the results success will increase if the CNN method is supported by adding extra feature extractions methods and classifying successfully the road potholes or even the presence of a plain road. Further, my friend will explain about the convolutional neural networks.
Convolutional neural networks is the main type of deep learning algorithm we are using here. A convolutional neural network is coming under artificial neural network that is specifically designed to process pixel data. It is used in image processing and video processing applications such as face recognition in mobile, style transferring, image quality enhancement, object detection in self-driving car, and gesture recognition. In CNN architecture, there will be different layers such as a convo layer, pooling layer, fully connected layer, softmax layer, output layer, and a dropout layer. So this is how the CNN architecture will work. Here the input image will be a pathole or a plain road image. The input image will be given and several actions, several operations will be there such as convolution, pooling, padding, stride, and it goes to the fully connected layer. After the fully connected layer, we will get our output. Let me explain about the layers about in detail. Convo layer. Convo layer is sometimes called a feature extractor layer because features of the images are get extracted within this layer. First of all, a part of image is connected to convo layer to perform convolution operation as we saw earlier and calculating the dot product between the respective field and the filter, which is a convolution operation. The result of the operation is a single integer of the output volume. It will repeat the same process again and again until it goes through the whole image. The output will be the input for a next pooling layer. Pooling layer. Coming to pooling layer is used to reduce the spatial volume of input image after convolution. It is used between two convolution layers. If it applies fully connected layer after convo layer without applying a pooling or a max pooling, then it will be a computationally expansive. So pooling is the only way to reduce the spatial volume of an input image.
After all the operations of convolution and pooling, it comes to the flattened layer where all the features of the image are extracted and basically classified, and they are put into a single line of a 1 cross n matrix which can be used to connect with all the layers and other neurons, that is called as the fully connected layer. A fully connected layer involves weights, biases and neurons. It connects neurons in one layer to the another layer. Then coming to the output layer, which is a softmax activation function. Softmax activation is the last layer of the CNN. It resides at the end of the fully connected layer. Softmax is used for binary classification and it is also for a multi-classification. In our case, we are using only two classifiers, that is a plain image or a pathole. That will be our output.
Coming to the operations used in a CNN, there are many operations, mainly convolution. Convolution is the pointwise multiplication of two functions to produce a third function. Here, the convolution means the pointwise multiplication of the input image with the filters to produce the output, which is called a convoluted feature or a feature map. This is the convolution example. From the input image, certain part each parts of the input image will be multiplied with the filter image with respect to the filter size, and the output will be obtained for each set of input layers, and the feature map will be in the size of n minus f plus 1 cross n minus f plus 1. Input is n cross n and filter will be f cross f. Padding. Padding is used to preserve the original dimensions of the input by avoiding the unwanted parts of the image and focuses on the main layers of the image. Types of CNN models, we are using three CNN models: manual net, AlexNet, LeNet. Among these three, AlexNet and LeNet are predefined, and manual net, as the name indicates, it's a manual one. Manual net is a simple architecture made by us for understanding the CNN operations and the workflow of it. We designed the manual net with a single convolutional and pooling layer and two fully connected layers. This is the architecture of a manual net that we made. First, we are presetting the image size as a 224 cross 224 cross 3, which is 3 channels, and we are going to one convolution layer with a 3 cross 3 kernel with 32 filters, and we are using reduce activation function. We are go to pooling layer with 2 cross 2 max pooling, and we are flattening the layer, which converts into a single convolution layer, and go to the fully connected layer, which represents as a dense 256 fully connected neurons, and again we are using a reduce activation function. Go to dense 2 fully connected neurons, and then we are using a softmax as a classifier, which classifies the output of one of two classes, that is pothole or plain road image, and the accuracy will be about around 60 to 80 percentage.
Moving to the next predefined architecture, AlexNet. It is one of the first convolutional network which used GPU to boost performance. AlexNet architecture consists of 5 convolutional layers, 3 max pooling layers, 2 normalization layers, 2 fully connected layers, and 1 softmax layer. Each convolutional layer consists of convolutional filters and non-linear activation function ReLU. The pooling layers are used to perform max pooling, which provides the main features of the image. This is the architecture of AlexNet. Here we preset the image sizes 224 cross 224 cross 3 channels, namely red, green, blue respectively. And we are doing convolutional property with 11 cross 11 kernel with 4 strides, which gives the image size as 54 cross 54 cross 96, whereas 96 is called filter. Then we are using a special operation called ReLU, and then we are doing max pooling by 2 cross 2 kernel with 2 strides, which gives the image sizes 27 cross 27 cross 96 filters. We are again performing same convolutional and pooling with various filters and kernel to extract more feature. We are performing max pooling, which extracts the detailed information from image. Finally, we are developing a flattened convolutional network with 4096 connected neurons in order to get a simple yet fully connected neuron network that are easily shared with its features with other networks in order to obtain best result. We are using dropout with 40% in order to reduce the size of the image for avoiding the unwanted features and to focus on the required features of the image. The accuracy for this model varies from 50 to 60%, which is not constant range of accuracy. It may vary depending upon the number of images given and also depending on the number of epochs provided for training. Hence, we move to another advanced architecture, which is LeNet, which will be now explained by our team member Vijay Shankar.
Moving on to the LeNet architecture, it is one of the earliest convolutional neural network which prompted the event of deep learning. After numerous years of analysis and plenty of compelling iterations, the end result was named as LeNet. LeNet CNN architecture is made up of 7 layers. The LeNet architecture consists of 2 sets of convolutions, activations and pooling, followed by a fully connected layer, which is another which can be connected to the other layers, and an activation layer, and finally a softmax classifier, which is used for the classification of the output images. Similar to the before architectures, the image size is presetted to 224 cross 224 into 3 layers and channels, and then we are performing convolution with 3 cross 3 kernel, which compresses the image size as 74 cross 74 with applying 32 filters and a ReLU activation function. And then we are performing max pooling in order to extract the main features of the images, thus reducing the image size as 34 cross 34 with the same number of filters. And then we are again performing the convolution with 3 cross 3 filters, and again we are extracting the images with max pooling with a size of 2 cross 2, and then we are finally making it as a flattened layer, which is a 1 cross n matrix, which is then connected to the 256 fully connected neurons, and with the activation function ReLU, which gives better classification accuracy due to its desirable properties. And then finally we are giving it to the softmax classifier, that which classifies the image output as either pathole or plain image. Let us consider this example of the image. This road consists of n number of pathholes, where there are many pathholes at different size, different locations, different shapes, different colors. All these images are extracted features. If you consider this small, this is called as a kernel, which is of 3 cross 3 size. When we are applying convolution, each of these boxes are taken and then the features are extracted. While coming to the pathhole images, these features are extracted particularly for that for the purpose of finding the presence of potholes while giving the input image in the Django framework, which you are implementing in the final stage. Coming to the system design, first we are loading the data by collecting all the different kinds of data sets that are required, which are pathhole or road images, and then we are importing the required libraries and packages for implementing the deep learning model, and then we are defining the model as sequential model. Thus we are defining the number of layers to be used, the number of nodes to be used in the model, and evaluation matrix. And then we are finally compiling the model by fitting the model with training data, test data, epoch, which is number of times the model is trained for better accuracy, and then batch size, which defines the number of images that are put in for every batch. When asked about the future scope of our project, in future, images can be uploaded in real time while driving cars, and then pathole prediction can be done. In the field of IoT, the driverless cars are to be the main feature of the IoT world. Pathole prediction using deep learning will play an important role by communicating with cars nearby, sharing the location of the potholes, reducing the occurrence of accidents, and saving lives. Maps can also be updated with the location of the potholes, similar to the traffic zones indications provided by the imagings from the satellite, which can be used in the field of driverless cars, thus avoiding accidents at most level. Concluding our project, we have applied different types of CNN models and compared their accuracy, and found that the linear architecture has the best accuracy of 80 to 95%. And then we are saving this file as a hierarchical file .h file, and then we are taking it and deploying it to the real-time Django framework for better user interface, where in real time the images can be uploaded, and then the output prediction will be happening there. These are the few of the reference that we used, and then we also learned about the convolutional neural networks from YouTube, and as well as we followed the reference models.